Hello again. Let's continue. As you know, or as you can guess, a large portion of operating system code is dedicated to managing input-output operations because of its importance to the performance of a system and because of the varying nature of devices. We use different devices and the loss of the an important part of the operating system or computers is uh, creating inputs or outputs. So we have a large portion of operating system code dedicated to that management. Recall from the beginning of this section, recall from the previous part that a general purpose computer system consists of multiple devices, all of which exchange data via a common bus. To solve this problem, we have DMA, which is direct memory access. As you can see from this figure, we have devices and we have memory. Also, we have central processing unit. In a general manner, we can say that if a device needs to use memory, it can ask the CPU and then CPU creates a connection between memory and the device. But instead of that, we generally use direct memory access. That means not only the CPU, also the other devices can directly access our main memory. It's called as direct memory access. So in I/O devices, the device controller transfers an entire block of data directly to or from the device and the main memory with no intervention by the CPU. Instead of sending the data to CPU, then the main memory, the device directly transfer the data to or from main memory and then create an interrupt. Okay, I managed to finish transferring data. So that means only one interrupt is generated per block rather than the one interrupt per byte. If you don't have direct memory access, that means your device has to create interrupts for every byte. Okay, I'm going to send a byte to memory, so I have to send that byte to CPU and CPU send that byte to main memory. Instead of that, we are using direct memory access, so your device controller can transfer a block of data instead of just one byte. So after that, it can just create one interrupt per block. So this is the power of direct memory access or direct memory access structure. Okay, now that we have discussed the basic information about computer system organization, actually you get some courses based on that architecture, you know, the organization or architecture of computer systems. For that reason, I just want to highlight some specific points. I'm not going to cover all the topics on computer organization, but we just highlighted some important points. So based on that information, based on that basic knowledge about computer system organization, now we are ready to talk about operating systems. An operating system provides the environment which programs are executed. So we can define an operating system like that too. We have application programs. Let's say I'm using just PowerPoint and Microsoft Teams that point for now. I want to use Microsoft Teams and PowerPoint. So for that reason, I need an interface between hardware and my application programs. So basically, we can say that an operating system provides an environment within which programs are executed. So basically, this is a very general definition, but it's correct in that manner. For a computer to start running, for instance, when it's powered up or rebooted, it needs to have an initial program to run. This initial program or bootstrap program tends to be simple and must know how to load the operating system and how to start executing that system. So basically, we know that all programs, including the operating system, must be loaded to main memory before executing. So for that reason, we have an initial program, a bootstrap program, which knows the address of the operating system and loads that operating system from secondary storage to main memory. To accomplish this goal, the bootstrap program must locate the operating system kernel and load it into memory. Once the kernel is loaded and executing, it can start providing services to the system and its users. Some services are provided outside of the kernel by system programs, and they are loaded into memory at boot time to become system daemons. Okay, they're not the part of kernels, but still that applications, that system programs serve users to some specific jobs. So for that reason, they have to be loaded they have to be loaded to main memory with the kernel, and they become system daemons. Basically, they are services provided outside of the kernel by system programs, but still they can be considered as the part of our operating systems. So basically, we can say that system daemons run the entire time the kernel is using. If there are no process to execute, no input-output devices to service, and no users to respond, an operating system will sit quietly, waiting for something to happen. For that reason, we call them as interrupt-driven. If you don't have any interrupt, that means you don't have any process to execute, or you don't have any IO devices to service, or you don't have any users to respond. So in that manner, in that case, the operating system will sit quietly, waiting for something to happen. Events are almost always signaled by the occurrences of an interrupt. We already described in that manner our hardware interrupts, and we already said that our operating systems are interrupt-driven. Another form of interrupt is a trap. Again, we already mentioned that a trap or an exception is actually can be defined as software-generated interrupts. Traps can be caused by an error, by a specific request from a user program. In this case, an operating system service be performed by executing a special operation called a system call. So basically, we have an error or we have a specific need. Based on that, the operating system, actually, we are requesting from operating system for a system call. So basically, in that manner, we can say that system calls are the main way we create an interaction between our application programs and the operating system. One of the most important aspects of operating system is the ability to run multiple programs. Because in general, a single program or user cannot keep the CPU or the IO devices busy at all times. Also, users generally want to run more than one program at a time. Multi-programming increases CPU utilization by organizing programs so that the CPU always has one process to execute or one job to execute. In a multi-programming system, a program in execution is called as process. So this is our main definition. While we are discussing process, actually we are indicating that point. In a multi-programming system, a program in execution is called as process. Actually, the idea is simple. The operating system keeps several processes in memory simultaneously. The operating system picks and begins to execute one of these processes. Eventually, the process may have to wait for some tasks, such as an IO operation, to complete. When that process needs to wait, the CPU switches to another process and start to execute that process, and so on. Eventually, the first process finishes waiting and gets the CPU back. As long as at least one process needs to execute, the CPU is never idle. It's going to continue with a cycle to schedule that jobs and execute that processes. Multitasking is a logical extension of multiprogramming. Still, the main idea is multiprogramming, but we have multitasking too, and multitasking is a logical extension of multiprogramming. In multitasking systems, the central processing unit executes multiple processes by switching among them, but the switches occur frequently, providing user with a fast response time. Actually, that processes are not executed on the CPU simultaneously, and actually it switches the processes, but it creates a fast response times. So it simulates that a position where we cannot understand that they are executing, that processes are executing in a cycle. We just consider that in our human eyes, okay, that programs are running concurrently. Having several processes in memory at the same time requires some form of memory management, which we are going to cover in the next chapters. The chapter 9 and 10 of this book is consists of the memory management. In addition, if several processes are ready to run at the same time, the system must choose which process will run next. Okay, we have lots of different processes. When the CPU is idle, it has to select one of that waiting process to execute. So that means making this decision is another important, let's say, purpose of operating system. So making this decision is called as CPU scheduling, and we are going to discuss that subject in chapter 5. Here we can see the memory layout for a multi-programming system. Okay, we have a memory here, we have a memory system here. Let's assume that this is our main memory. First of all, on the boot time, Bootstrap program has to load the operating system. Actually, the operating system here is our kernel and system daemons. While the computer is running, that kernel has to be executed. And then when we want to execute a program, we know that we have to load that program to main memory. The program on the execution step called as processes. So that means we can store more than one process on the main memory. So based on that, our CPU can choose one of that process to execute when it's idle. So we can consider a memory layout for a multi-programming system like that. Since the operating system and its users share the hardware and software resources of the computer system, a properly designed operating system must ensure that an incorrect program cannot cause other programs to execute incorrectly. Okay, we are sharing different users and different programs. One of that programs can create a problem. We have to ensure that that problem created by a program cannot be affect other programs. So in order to ensure the proper execution of the system, we must be able to apart between the execution of operating system code and user-defined code, because the operating system is important for us. If there could be a problem on an application program, it's not important. Actually, it's important for that program, but it's not going to affect other programs too. If that problem affects the operating system, it's going to affect all your systems and all your programs. For that reason, we have to distinguish the operating system code and the user-defined code or application code. So that means at the very least, we need two separate modes of operation, and they're called as user mode and kernel mode. A bit called the mode bit is added to the hardware of the computer to indicate that the current mode, kernel 0 or user 1. So basically the definition, the mode bit provided by hardware. If the mode bit is 0, so all the hardwares can understand that it's running on kernel mode. If it's 1, all the hardware and system understand that, okay, this code is running on user mode. When the computer system is executing on behalf of a user application, the system means in user mode. However, when a user application requests a service from the operating system via system call, the system must transition from user to kernel mode to respond to the request. So, okay, our programs are running on user mode, but when we need an I/O intervention, for example, or when we need a specific request from operating system, we have to create a system call. Based on system call, operating system, actually we change the mode from user mode to kernel mode, and operating system serve that our request, and we can return to user mode to fetch that data again. So this is the transition from user to kernel mode. This, let's say this is our application program, user program, and on the bottom we have a kernel. We are executing our program. At some point we need, let's say, an I/O intervention. For that reason, our program, our application is going to create a trap, and we are going to pass the control to operating system. So basically we are creating a transition from user mode to kernel mode. So operating system executes that system call and then return to the system call, return to the calling environment. In this case, it's our user process. So if you want to make operating system processes, let's say managing resources or creating or handling interrupts, so that means you have to change your mode to kernel mode first, and then when you pass the control, you have to change the mode to user mode again. We must ensure that the operating system maintains control over the CPU. We cannot allow a user program to get stuck in an infinite loop or to fail to call system services and never return control to the operating system. To accomplish this goal, we can use a timer. A timer can be set to interrupt the computer after a specified period. So the period may be fixed or variable. A variable timer is generally implemented by a fixed rate clock and a counter. The operating system sets the counter. Every time the clock ticks, the counter is decremented. When the counter reaches 0, an interrupt occurs. So we don't need to wait the process to get done its job. We don't need to wait until the process terminates. In a specific time, using a timer, we can create an interrupt, and based on that period, we can change the process which is running on the CPU. So based on that, we can maintain the CPU time provided to each process. As we have seen, an operating system is a resource manager. The system's CPU, memory space, file storage, and I/O devices are among the resources that the operating system must manage. We will start with the process management. Basically, a process is a program in execution, as we already stated. A program is a passive entity, but process is an active entity. Actually, this is the difference between a program and a process. A program is a passive entity, actually stored on your storage, but a process is an active entity. That means a running instance of a program. For now, you can consider a process to be an instance of a program in execution. A process needs certain resources, including CPU time, memory, files, and I/O devices, to accomplish its task to terminate its execution. These resources are typically allocated to the process while it's running. When the process terminates, the operating system will reclaim any reusable resources. Okay, we are going to execute a process. That process needs some resources, so operating system is going to allocate that resources to that process. But when that process is terminated, we have to reclaim that resources back, because we are going to use that resources again and again for different processes. We have to emphasize that a program by itself is not a process. A program is a passive entity, like the contents of a file stored on disk, whereas a process is an active entity. A program stores on your disk, but when you want to execute that program, let's say when you want to open that program, you have to load that program to the memory. So that means you are going to creating processes. A single threaded process has one program counter specifying the next instruction to execute. Okay, you created your process, you loaded your program to memory. If it's a single threaded process, it has just one program counter and it's going to specify the next instruction to execute. The execution of such a process must be sequential. The CPU executes one instruction of the process after another until the process completes. You can consider that like a simple C program. We have statements. The CPU has to execute that statements in the right order sequentially. On the other hand, if you have a multi-threaded process, a multi-threaded process has multiple program counters. You need more than one program counters, and each program counter has to point to the next instruction to execute for a given thread. Every thread has its own program counter. And also, we can directly say that a process is the unit of work in a system. For that reason, we're just calling at every identical instance of program as processes. A system consists of a collection of processes, some of which are operating system processes, and the rest of are user processes. But we describe all that program instances executing on our system as processes. All these processes can potentially execute concurrently by multiplexing on a single CPU core or in parallel across multiple CPU cores. The operating systems is responsible for these activities in connection with process management, creating and deleting both user and system processes, suspending and resuming processes, providing mechanism for process synchronization, providing mechanism for process communication, providing mechanism for deadlock handling. So we are going to discuss these activities on process management techniques through chapter 3 to chapter 7. So actually, a huge amount of these course will be about process management. From starting to chapter 3 to chapter 7, we are going to discuss different levels and different aspects of process management on operating systems. The next resource we are going to talk about will be memory. As you know, the main memory is central to the operation of a modern computer system. Sorry. For a program to be executed, it must be loaded or it must be mapped to absolute addresses and loaded into memory. So we generally say that we have to load the program to memory, but Actually, in the backend, we have to map our program instructions to the memory, to the absolute addresses, absolute physical addresses of the memory. As the program executes, it accesses program instructions and data from memory by generating these absolute addresses. Because when you execute, while you are executing your process on CPU, and let's assume that CPU needs to reach the next instruction, or CPU needs to fetch some data, it has to know to absolute addresses of that data or instruction. Um, Eventually, the program terminates. Its memory space is declared available, and the next program can be loaded and executed. The operating system is responsible for these activities in connection with memory management, keeping track of which parts of memory are currently being used and by whom, deciding which processes and data to move into and out of memory, and the last part, allocating and deallocating memory spaces as needed. So we are going to discuss the memory management in this manner too. To make the computer systems convenient for users, the operating system provides a uniform, logical view of information storage, which is called as file. The operating system abstracts from the physical properties of its storage devices to define a logical storage unit. The operating system maps these files, the storage units, onto physical media and access these files using the storage devices. The operating system is responsible for these activities in connection with the file management, which are creating and deleting files and directories, primitives to manipulate files and directories, mapping files onto secondary storage, backup files onto stable or non-volatile storage media. So another important resource management goal or aim of operating system is file system management. So that means we first of all need to cover memory management with the secondary storage part, and then we have to discuss how file systems can be managed by operating system. And this is the second part. As we have already seen or stated, the computer system must provide secondary storage to back up main memory. Most modern computer systems use HDD and SSD devices as the principal storage media for both programs and data. And most programs are stored on these devices until loaded into memory. The programs then use the devices as both the source and the destination of processing. Our data are stored on secondary storage, so that means it's our source. Also, we are going to write that data to secondary storage too. So that means it's also a destination for us. So the proper management of secondary storage has a central importance on a computer system. The operating system is responsible for these activities in connection with secondary storage management as mounting and unmounting. We have to mount or unmount our secondary storage devices. We have to manage the free space on mass storage. We need storage allocation, disk scheduling, partitioning, and protection. So these activities will be our main topics while we discuss the mass storage management of operating systems. The next thing, we need to talk about is cache management. Caching is an important principle of computer systems. Here's how it works. Information is normally kept in some storage systems, such as main memory. As it is used, it's copied into a faster storage system the cache on a temporary bias or temporary basis. When we need a particular piece of information, we first check whether it's in the cache or not. If it is in the cache, we can use the information directly from the cache. If it's not, we use the information from the source and putting a copy of that source in the cache under the assumption that we are going to need that data again. Because caches have limited size, cache management is another important design problem. So we have to be careful. We need a careful selection of the cache sizes, and a replacement policy can result in an increased performance. So we are going to discuss the caching methods too. In an storage structure like that, the same data may appear in different levels of storage systems. Here we have an example. Suppose that an integer a that is to be incremented by 1 is located in file B, and file B resides on hard disk. We have a file B. On file B, we have an integer a. We want to increase the value of a by 1, but that file resides on hard disk. The increment operation proceeds by first issuing an I/O operation to copy the disk block on which A resides in the main memory. So we have to copy A to main memory. This operation is followed by copying A to the cache and to an internal register. At the first point, the A resides on the disk. So if we want to make an operation on A, we have to move it to main memory, then cache, then the hardware register. Thus, that means the copy of A appears in several places on the hard disk in main memory, in the cache, and in the internal register. We have different copies of the same integer, the same variable. Once the increment takes place in internal register, the value of A differs in the various storage systems. It's different on the main memory and cache, but we make the increment on the CPU, so it has a different value on hardware register. So multitasking environments must be careful to use most recent value. Okay, we make an increment, we increase the value of A and assume that another process wants to use A. So we have to be careful about use the most recent value of that variable, in this case A. The situation becomes more complicated in a multiprocessor environment. In such an environment, a copy of A may exist simultaneously in several caches of several central processing units. Since the various central processing units can all execute in parallel, we must make sure that an update to value of A in one cache is immediately reflected in all other caches where A resides. This situation is called cache coherency, and is usually a hardware issue and handled below the operating system level. But in some points, we have to consider we have a risk like that. One of the purposes of an operating system is to hide the some peculiarities of specific hardware devices from the user. So this task can be done by the I/O subsystem. The I/O subsystem consists of several components. A memory management component that includes buffering, caching, and spooling. A general device driver interface and drivers for specific hardware devices. Okay, all of this stuff was part of the resource management. We considered process management, secondary storage management, memory management, caching. But all of this stuff was part of the resource management. There are these also IO subsystem. They're all resources and the operating system responsible to managing that resources. Now we have to say a few things about security and product protection, because security and our operating systems has to provide some level of protection and security too, not just resource management. Protection is any mechanism for controlling access of processes or users to resources defined by the operating system. And security is defense of the system against internal and external attacks. Protection and security require the system to be able to distinguish among all its users. Most operating systems maintain a list of users, actual user names, and associated user identifiers, generally called as user IDs, or in some systems it's called as security IDs. In some circumstances, we wish to distinguish among sets of users rather than individual users. In this case, group functionality can be implemented as a system-wide list of group names and group identifier. Okay, we have users and user IDs, but actually they could be a part of a group. We can manage we can create the protection or security mechanism based on groups too. For that reason, we need group functionality, and every group needs an ID called as group ID. In the course of normal system use, the user ID and group ID for a user are sufficient. However, a user sometimes need to escalate privileges to gain extra permissions for an activity. The user may need access to a device, let's assume that's restricted, for example. So operating system provide various methods or mechanism to allow privilege escalation. Okay, we have a user, let's say it has some privileges, but in some point that user or user application may need access to device that's restricted for that user or that group. So we have to create some mechanisms to manage that privileges. And the virtualization. Virtualization is a technology, as you know, that allows us to abstract the hardware of a single computer into several different execution environments. So it creates the illusion that each separate environment is running on its own private computer. Actually, they're running on the same hardware, but it creates an illusion that each separate environment, each separate operating system is running on its own private computer. Virtualization allows operating systems to run as applications within other operating systems. Actually, they are operating systems, but in some point of view, we can say that, okay, these operating systems are applications, application programs on other operating systems. At first look, there seems to be little reason for such functionality, but the virtualization industry is vast and growing. Here you can see an abstraction of virtualization. Our textbook also covered computer system architecture and computing environments at this point. As I said before, I know most of you are familiar with that, so I'm not going to cover that sections now. But I want you to read the computer system architecture section of our textbook. Also, there's another section about free and open source operating systems. You may want to read that section too, but I'm not going to cover it directly on this course. Okay, we have on textbook, we have computer system architecture and computer environments sections. Also, we have free and open source operating system sections. I want you to read that sections from textbook. We turn next to a subject central to operating system implementation, the way data are structured in the system. In this section, the textbook describes these data structures used extensively in operating systems. Actually, they're based on C programming, and we already covered lots of them in our algorithms and programming course. Also, you get the data structure course. So that means you already know some data structures such as a single linked list, double linked list, circular linked list, etc. But if you do not remember the details on these structures, you can take a look at a textbook. We have another section on the textbook introducing kernel data structures. But as I said, I'm not going to cover that data structures now because, okay, I'm going to serve some examples using C programming language. We need to know some basic kernel data structures, some basic data structures, but I'm not going to cover them directly in this course because our main purpose is to focus on operating systems. And that's it for this week. Sorry. Do you have any question? Geçen sene verdiğim ödevleri paylaşır mıyım? Paylaşırım. Yani bu hafta içerisinde paylaşayım en azından ilk ödevi. Bu hafta aslında kısa bir giriş yapmış olduk. Nelerden bahsettik? Aslında hani organizasyona ve mimariye çok fazla girmeden yine de elektronik bilgisayar sistemlerinin bizim için önemli olan birkaç parçasının altını çizdik. Çünkü bu kavramları kullanacağız. Bu kavramlar üzerine işletim sistemini bina edeceğiz. Yani zaten donanım üzerine bina ediyoruz ama hani bazı temel kavramları yeniden hatırlamak lazım. Çünkü aslında temel olarak işletim sistemi dediğimiz şey en başta donanım kaynaklarının paylaştırılması ve yönetilmesini sağlayan, bunu sağlayarak kullanıcının kendi programlarını çalıştırabilmesi için bir arayüz sağlayan bir programlar bütünü olarak düşünebiliriz. Bundan bahsettik. Ardından aslında bu dönem boyunca hangi konular üzerine yoğunlaşacağımızdan bahsettik. Proseslerden ve proses yönetiminden, proses scheduling'den bahsedeceğiz. Memory management'tan bahsedeceğiz. İşte secondary storage'ı nasıl yönetebiliriz, oradaki verilere nasıl ulaşabiliriz. Bunlardan bahsedeceğiz. Input output'tan zaten her birinin bir parçası olarak bahsetmemiz gerekecek. Ardından vaktimiz kalırsa dosya sistemlerinden ve kısaca protection ve security'den bahsedip dönemi kapatacağız. Ama odak noktamızda proses ve proses yönetimi, ardından da memory ve memory yönetimi olacak. Bu haftayı böyle kısa bir giriş yapmış olarak düşünelim. Önümüzdeki hafta daha detaylı olarak işletim sistemi konseptlerinin neler olduğundan bahsederek devam edeceğiz. Hemen sonrasında proseslerden bahsetmeye başlarız. Var mı sorusu olan? Soru yoksa bu haftalık kapatalım arkadaşlar. Önümüzdeki hafta görüşmek üzere. Hoşça kalın. Kendinize iyi bakın.